And hello, welcome YouTube, or welcome to this video. It's a continuation of turbulence modeling, and we are going to talk more about the theoretical background behind some of the LES models in continuation, so that we can have a more comprehensive review of the turbulence models used in many CFD codes, and such as OpenFOAM. So in the last video, we were talking about several of the Reynolds average Navier Stokes models. For example, Kepsilon. Okay, so let me zoom in. It's a Kepsilon model. It's a K omega model. Okay, we have K omega SST. Shear stress transport. And we have a Spalart Allmaras model. Okay, so these are used for several different kind of applications, and they're all Reynolds average Navier Stokes, or more specifically, the unsteady version of Reynolds average Navier Stokes. So these are unsteady Reynolds average Navier Stokes. Why is it so? Because in classical Reynolds average Navier Stokes, you want to do an average of the time average of the velocity. So it's 1 divided by delta t. So integrate from 0 to infinity u of t dt. Okay, so delta t. Alright, so this is the time average, right? Okay, so for Reynolds average Navier Stokes, we have t going to infinity, right? So limit delta t going to infinity, alright, of this whole thing. So that's what Reynolds average Navier Stokes is. I mean, in the true sense of the word, if you have let me find paint. Yeah, if you have let's see. Yeah, if you have, let's say, in one spot, u of t, with t, alright, you have t here. So you have several fluctuations, right? And you try and average all of these fluctuations out over time. Doesn't matter what they are. I mean, it could be even like this. Let's say you were kind of toggling a valve. You're toggling a valve on and off, and it's still giving you this pattern. Then of course, in that pattern itself, you will have a lot of this turbulence fluctuation. Of course, I'm not exactly drawing it very well. Okay, so if you were to do this time averaging, it would actually get rid of all these bumps. So let's say, right, if you have this and you have some kind of valve, right, you have a valve that you're adjusting for turbulent flow in the pipe, and then the velocity is somewhere in the pipe as you turn the valve up and down will be something like this. So Reynolds average Navier Stokes will get rid of all the bumps. All right, Reynolds average Navier Stokes will get rid of all these bumps, but unsteady Reynolds average Navier Stokes, which is something you probably use in OpenFOAM or some other CFD codes, you don't get rid of all the bumps. Equals infinity, right? So maybe you'll try and get rid of some of the bumps, and that's what you have. And this is also called very large eddy simulation. Alright, VLES. Okay, so if you don't have your delta t, which is your you don't have your time dependent term going to infinity, you call this a very large eddy simulation. Okay. Unfortunately, there are some deficiencies to Reynolds average Navier-Stokes. For example, they don't, for like complex machinery and complex flows, they don't capture all the physics behind it. They do not capture all these eddies coming out, and the eddies are weaknesses, and the flow results, alright, are only as good as the model of turbulence. So that means when you use turbulent viscosity to model turbulence, or turbulent kinetic energy, dissipation rate, etc., etc., your flow that you kind of compute in your CFD code is only as good as those models. And from what we know, these models are not good in every case. So for example, here we can take a look at some of the weaknesses. Alright, so weaknesses of some Reynolds average Navier-Stokes, or unsteady Reynolds average Navier-Stokes. So this one has a unsteady Reynolds average Navier-Stokes has a time dependent term in the Navier-Stokes equation, but it still models viscosity in pretty much the same way as Reynolds average Navier-Stokes. Okay, this is also called, it's commonly called very large eddy simulation. Both of them are almost similar enough. Perhaps you may find some nuance in the literature, but I'm not going to go into that. I will just assume for the sake of these videos that they are the same, and they are pretty much in general the same. Yeah. So Kepsilon model, it doesn't do adverse pressure gradients well. About wall boundary conditions not good. As good as K omega. Okay, K omega has another weakness. It's the free stream omega boundary condition must be specified. Okay, so and you don't really know what that is all the time, and the flow is sensitive to this BC. K omega SST blends K omega and K epsilon. Okay, but this is one of the best, one of the most popular, I would say. I don't know whether you would say best. Different situations, different models are better. Okay, so these are complex flows. Not good. Okay, so it's good for some flows and not good for others. For example, airfoil. Well, no. Yeah, some complex flows you cannot model those properly. Cannot model some complex flows properly. For example, turbo machinery. Right? It's like turbines, jets, everything. Yeah, so it's not accurate enough for those. Likewise, the Spalart Allmaras model also suffers from the same weakness. Okay, and of course it's inaccurate in some other flows. I mean, this is accurate across all of them, and one of the most important things is that all of these are based on empirical models of wall functions, and these are not universal. So none of these models are quite universal, and the only universal model is DNS, which is direct numerical simulation, but that is too computationally expensive. And yeah, so that's why we still want to look at LES modeling as an alternative way. Okay, so why LES? As I said just now, Reynolds average Navier Stokes has a lot of empirical constant, and the equation used for one flow may not always match, may not always be suitable. Okay, the equation constants used for one flow may not be always suitable for that of another flow. So this is unsteady Reynolds average Navier Stokes, yeah. And already said just now. And who said the other same? I think it's Spalart and Allmaras. They're talking about a hybrid Reynolds average Navier Stokes and large eddy simulation approach, which we may want to discuss in further videos, but we'll just do LES for now. And DNS, while accurate, is too impractical. So let's move on to some other models of large eddy simulation. And we studied the Smagorinsky model before, very briefly, because it's so simple. It's one of the simplest LES models out there, used for atmospheric boundary layers. Alright. Used originally for atmospheric boundary layers. It's meteorology. Alright, so if you want to model flows in the atmosphere, they use this model very early on. And yeah, so the turbulent viscosity is it's modeled like this. It's a C Smagorinsky squared into delta squared. This is C Smagorinsky CS into delta. C Smagorinsky times delta is some length scale, and this is some filtered rate of strain. So remember, well, for Reynolds average Navier Stokes, you do a time averaging. Well, filtering is something slightly different. I briefly covered that in the videos earlier videos where I introduced basic Smagorinsky model. So yeah, the problem is that you can't use this Smagorinsky coefficient, the Smagorinsky coefficient. You cannot have it generalized over all flows. Some flows use 0.17, 0.15, 0.2, 0.25, and all depends on the situation. I think for pipe or duct flow, CS or C Smagorinsky is approximately 0.11. So you can see there's a very large variance in this this constant, and we know that this constant isn't very good across all cases. So for an airfoil, a wing, for example, and a pipe flow and a boundary layer flow, all of these may have different C Smagorinsky, and it kind of limits the use of this model. While it's very simple to implement, you cannot use it all around. So it's good for turbulence modeling in meteorology, but not very good otherwise. So how can we deal with this? Okay, so we're going to introduce something new that builds on the Smagorinsky model, and the idea is to try and have this Smagorinsky coefficient dynamically calculated. We call it a dynamic coefficient, and it's based on a similarity approach. So what is this similarity approach? Okay, so I want to first introduce you to a picture of turbulence. So let's do firstly a picture of turbulence. So in a turbulent flow, for example, right, we have very large eddies and eddies like so. Then we have medium-sized eddies, and we have very, very small eddies. Alright, so in turbulence, there are large eddies, medium eddies, okay, small eddies. Okay, this is very, very general. I'm just arbitrarily giving you 3 categories because there are like 3 sizes we are very familiar with. You can kind of divide them out using a number, a characteristic number or size or what have you. Okay, but these are just to give you a general idea of what's going on there. So the similarity approach is this, okay? So since you have large eddies, right? You have large eddies, and then you have medium eddies, and then you have very small eddies, right? We can say, okay, the similarity is this. The similarity is this. Okay. Similarity is this. The way that the large eddies interact with the medium eddies is very similar. Okay, large medium interaction. It's very similar to medium small interaction. Okay, so we have a large medium interaction going on, and that is very similar to the medium small interaction. What are the primary ways they interact? Okay, so right from remember I was discussing that when you have a shear in this average velocity, okay, this will tend to generate turbulence, right? This will tend to generate turbulence. And basically, if you talk about energy, an energy cascade, the turbulence shear will extract energy from the mean flow. So it takes energy from the mean flow U and it turns it into, it turns it into kinetic energy of the large eddy. Okay, the kinetic energy of this large eddy. And likewise, the large eddy can sometimes break up into small eddies or pass some of its kinetic energy over. So these medium eddies will also have some kinetic energy. And likewise, medium eddies can pass on their kinetic energy to the small eddies. Okay? Hopefully that's clear. And of course, this thing happens, it can happen 2 ways. Sometimes the kinetic energy of small eddies can come back to the medium eddies, and it can also come back to the large eddies. And this is what in LES people call backscatter. Alright? Because the kinetic energy is scattering back. And of course, from the smallest eddies, you transfer kinetic energy into heat. And at that time, I think the backscatter is so small, I think you can just neglect it. And then thermodynamics doesn't always allow for a net flow of energy like this, from heat to kinetic energy. So second law doesn't allow for that. But this one is by and large ignored, so insignificant or small. And the idea is to use this similarity of the large and medium interaction to guess the coefficient, okay, the dynamic coefficient. So now we will use the subscript D to denote a dynamic coefficient. We take inspiration from the large medium interaction to generate a dynamic coefficient for the medium small interaction. Now this is what is known in the community or LES community as the dynamic model. So I'd like to show you that here in CFD Online. Okay, CFD Online is here, and we can do this. Okay, dynamic model. Okay, LES dynamic model or Dynamic Smagorinsky, because this actually builds up from Smagorinsky's model. Okay, so this picture of turbulence I will just put copy and paste here, and yeah, so I'll just put it here, and I have gotten requests to actually post these notes. I shouldn't use this snipping tool. Give a higher resolution. I'll just use select in paint. Yeah, I have received requests that I post some of these notes online in my previous videos. I mean, once I finish in time and make some corrections and what have you, and also I need to scrub the notes of all copyrighted material as far as possible, then I mean I can post it online and it'll be on GitHub, but I don't have it now because I'm not finished with this series as of the time of recording of this video, but hopefully I hope to have it up and on GitHub, but that's for another time. So yeah, anyhow, most important thing is you get the idea of where the gist of what this dynamic model is about. It is trying to use the interaction between the large and medium eddies. Alright, so this is how I think the scale should be. Between the large and medium eddies, how they interact by passing on kinetic energy to one another. It's how the medium and small interaction, they assume the way they interact is the same. That's the large idea, the big idea, and they use that to try and generate some sort of coefficient. How is that done? It's a little more complicated than what I just said, but just bear with me. We'll try to go through some of these equations in the following videos. So I'll just stop for now. Thanks for watching. I'll see you guys again. Bye bye.